All right, college algebra. We're looking at inverses and exponential functions today, section 4.2a. If we look at number 1 here, this is a relation. We see 3 ordered pairs in this relation. All right, an inverse is a relation where we have the x's become y's and the y's become x's. And so on this right here, this is real simple. My x is -4, my y is 7. So on the inverse, I'm just going to show you the answer down here. 7, -4. I just switch these numbers. In this order pair 1, 2, I'm going to switch them 2, 1. And then here I got 4, 8. I'm going to switch them 8, 4. That's the inverse function. Okay. It's real simple to do something like this. Here's one here. 4, 3. Okay. 2, 7, 3, 2, 6, 3. This one here is not 1 to 1, so it does not have an inverse. The reason it's not 1 to 1 is we have a repeat on the 3 here. So if I switch these, I'm going to have 3 with 4, and I have 3 with 6, which is not a function. So it's not 1 to 1. What 1 to 1 means is that each x has only one y, and each y only has one x. So if you have any repeats on here on value, then it's not 1 to 1. So like right here, we have the repeat on 3's. Now, the way this is right here, this would be a function. Yeah, this is a function, but it's not a 1 to 1 function. So answer is B here. The function is not 1 to 1. Inverses can be used to solve equations. Here's an example right here. Suppose I have y equals 2x plus 1. And I want to put different values in for x. So I want to put in, say, 4, 6, -2, and 1. I want to put these values for x in and get what the y value is. So 4, I can put 4 in. 2 times 4 is 8. 8 plus 1 would be 9, so y would be 9. Okay. If I put 6 in, 2 times 6 would be 12, plus 1 would be 13. If I want to do -2, 2 times -2 is -4, plus 1 would be -3. And if I do 1, 2 times 1 is 2, plus 1 would be +3. So that's really easy finding these values just by plugging those in. But suppose I wanted this. Suppose I have these y values, like 7 and -3 and 12 and 15. Suppose I have these y values, and I want to get what x values make those y values. Well, then that becomes a challenge, because if I put 7 for y, then I have to solve this equation. And if I put -3 in for y, I got to solve an equation. So I have to solve an equation for each one. So in this instance here, it would be nice if I had the inverse. All right, so that's what we're going to be doing here, finding the inverse. To find the inverse, it's 4 steps. 4 steps. Now, this is already in y, but the first step, if it's a function, we want to change f of x to y. Well, this I made up here, it's already a y. So this first step is not really needed for this problem we're doing. Second step, I swap x and y. So I would swap them. Okay, so in this problem I'm doing, if I swap my x and y, I'll have this. I'll have x equals 2y plus 1. Okay, if I swap my x and my y. All right, then third thing I would do is I would solve for y. So I'd solve for y here, which means I would -1. So I have x minus 1 equals 2y. Then I would divide by 2. And then y would equal, I can just leave it like that, x minus 1 divided by 2. There you go. I solve for y. And then step 4, I would change y to f inverse of x. This f negative 1, this is like a negative 1 exponent. That's just f inverse of x. So I would just change my y to f inverse of x. So f negative 1 of x equals x minus 1 over 2. And this is the inverse. And so what that means is these y values I wanted, I could put those in as x values like I did over here then a while ago. So I have the x, so the 7, negative 3, 12, and 15. Now I could put those in as x values in this function. So like if I do 7 minus 1 would be 6, 6 divided by 2 would be 3. And if I put negative 3 in there, negative 3 minus 1 would be negative 4 divided by 2 would be negative 2. And then 12 minus 1 is 11, 11 divided by 2 is 11 halves, or 5.5. And so it becomes a lot easier, more simple. 15 minus 1 is 14, divided by 2 is 7. So I found these values I was wanting a lot easier because I had the inverse function. And that's what inverses can do. All right, so we have a couple of these we're going to do here. So we see this function here. Determine whether the function is 1 to 1. If so, write the equation for the inverse. Okay, well, f of x is x to the third minus 1. All right, this is 1 to 1. The ones you have to watch out for that are not 1 to 1 is if you have an even power like x squared. X squared, not 1 to 1. Okay. So this one is 1 to 1. So it should have an inverse. So we want to find out what this inverse is. So we're going to do the 4 steps like I just did a minute ago. I'm going to change f of x to y. I'm going to swap x and y. I'm going to solve for y. Then I'm going to change y to f inverse of x. So what I'm going to do is I'm going to fold this up a little bit so you can have these notes to look at, okay? All right, there's my notes. Okay. And so we're going to do this problem here. Now the problem was f of x equals x to the third minus 1. Okay, so first thing we do is we change f of x to y. So we're going to change this to y. That's step 1. All right, now step 2, we're going to swap the x and y. So now y becomes x and x becomes y. Okay, and now I have step 3. I have to solve for y. So I need to solve for y. Well, let's see, this plus 1, I'm going to have to, or this minus 1, I'm going to have to add 1 to both sides. That gives me x plus 1 equals y to the third. And now to get rid of this third power, I would do a third root. I didn't need to put the parentheses on there, I guess. So this third root cancels the third power, so I have the third root of x plus 1 equals y. And there you go, I solved for y. All right, I'm about to sneeze. Oh my goodness. You know, usually you don't sneeze but once. You always sneeze twice, or I do, but we'll see if it takes place. All right, now, step 4, I change y to f inverse of x. So y, and I'm going to swap the sides here. F inverse of x equals the third root of x plus 1, and there's my inverse function. Okay? So I'm going to write that right here. F inverse of x equals the third root of x plus 1. Okay? And that's my inverse function. And if you see my answer down here, well, you are right. You are correct. Now, this says choose the correct graph of the function and its inverse. Choose the correct graph. All right, so when you graph the inverse and its function, there's always a diagonal line. Like if I put this line through here, that makes it symmetric. This one's looking like A. If I draw that diagonal line here, it doesn't really look like this is symmetric about that line. One thing is when they cross, see right here where these two cross, it's not on that line. Right here where they cross, right there is on the line I just drew. See, if I draw this line and it just goes straight up diagonally through here like this. See, these cross right there don't look like it crosses on it. Now, if you want to be more specific, you could take a value or two and put it in. Now, what you, I think on these, you can make them bigger on the screen to look at them a little bit closer. Obviously, on this paper, I can't do that. But what you can do is you could like take a value like 0 and you put it in. So like if I put 0 in here, 0 to the third power is 0, minus 1 would be negative 1. So if x is 0, y would be negative 1. So that looks like right here on this blue one. Okay. Now if I put another value in like 1 to the third power is 1, minus 1 would be 0. So at 1, it's 0, which looks like this value right here. And like I said, you could blow these up to make a better picture. And if you do the inverse, you do the same thing. So if I put 0 in for x, then I'd have a third root of 0 plus 1, which would be 1. So if I put 0 in for x, then I'd have 1 for y. So that's this red one. So that'd be 0, 1, which is right here, see? And it really is kind of hard to see on this. Maybe I'll do one on the screen here that you can see it maybe a little better. Okay, now we'll go on this one, finish it up. Part C says, what's the domain and range of the function and its inverse? All right, so the function is the blue one. The inverse is the red one. So if I look at the blue one, what's the furthest to the left that it goes? Well, it's going down forever, but it's going over. So that's going to be negative infinity, and it's going to go negative infinity to positive infinity. That'd be the domain. The range, up and down, same thing. All right. What about the inverse? All right, here's one thing about the inverse. The inverse, if you remember, you're swapping your x's and your y's. Okay? So that means my range would be the same as the domain. And then my domain be the same as the range. Okay? So if this was like 2 to infinity, well, then this here would be 2 to infinity. And if this was negative infinity to 3, well, then this would be negative infinity to 3. Okay. Oh, I didn't have it on the screen. I'm sorry. All right, so your domain of your function would be the range of the inverse. And the range of the function would be the domain of the inverse. Okay. We'll do another one here. All right. This is a good one here now. See, this is x squared plus 5. This is not 1 to 1. So this is going to be b here. The function is not 1 to 1. We got x squared. Anytime in a function you have a square or an even power, it's not 1 to 1, so it's not going to have an inverse. All right, so it's not 1 to 1. Now, if you graph it, well, the function is not 1 to 1, thus the inverse does not exist. So that's D. It's not 1 to 1, so the inverse does not exist. All right. Then what's the, give the domain and range of the function. All right, so the domain, all right, so if you look at your function here, it's a parabola. It's this blue one right here. This is x squared, it's plus 5, so it's going up 5. So I think this right here is the graph of the function. All right, so just like we've done before, the domain, negative infinity, positive infinity. If anybody misses that, man, I'm going to be disappointed. The range, it looks like it goes from 5. See, it's up 5, so it goes from 5 to infinity. Okay, so there's the domain of the function. Now, what's the domain range of the inverse? Well, it's not possible because it's not 1 to 1. Okay, I didn't have it on there either. Okay. Let's see here. We'll do it on the screen just so you can see it a little better. Okay. All right, so this one right here, all right, if I change it to y, I'm doing this in my head. I'll add the 3. So I'll have y, I'll swap x and y, so I have x plus 3, and I have a third root. So this is going to be a third root. So I just click this. This is going to be a third root. This is going to be x plus 3 inside here. Okay, I don't know, is that the same problem we did all ago? It was similar. The one we did all ago, this was x to the third minus 1. All right, so check my answer. All right, we're good. All right, now, here's what I want you to see. I'm just going to do this part right here, and I'm going to quit. All right, so which one of these is the correct graph? Okay, so you got to look and see. Now this one right here, see if I draw that diagonal line I'm talking about, I can see that these two are not going to cross on the diagonal line. Now you can blow this up several times and make it bigger and bigger. Okay. And see that diagonal line, it's going to go from this corner right here to this corner, to this corner, to this corner, to this corner, to that corner, and that's not where this intersection occurs. So B is not right. Now A here, let's make it bigger. Let's click on that, and if I click on this bottom one, it gets big like this, so you can see on the screen. And look here, see, I'm thinking this is the answer right here, because see, as I go from this corner to that corner, it looks like it crosses right on that line. Yeah. Now another way you could tell is like where it ends right here. All right, this is at 10, and it looks like it's a little bit more. See, I think these are 2, 4, 6, 8, 10. See that? 2, 4, 6, 8, 10. So if I go to 10, it's a little more than 2. All right, so if I switch those values, a little more than 2 should go up 10. See, that if I switch the two values, the graph hits that. So like right here, it crosses 0. It crosses the axis here at almost 2. Well, on the axis here, it's almost 2. So see, this is the right one right here. This is correct 1A. See, if you click on this one here for C and look at it, see, you clearly tell that's not going to be on the diagonal. See, if you look here, if you go from this corner to that corner to that corner, see, the intersection is not on this diagonal line, and it's got to be on that diagonal line. So that tells me right there, these are not inverses. Okay, so the answer is A. All right. And then you do your domain range. And I think my domain range, see, this goes down, which means it goes left forever, and it goes up, which means it goes to the right forever. So the domain is negative infinity, positive infinity, and the range down forever, up for, yeah, they're both negative infinity, positive infinity. Okay, so I think that's all I'm going to say about that. If you have questions about those, just holler at me. I'll try to help you some, but we're not doing very many, just a couple of those. All right, then we're going to shift gears. Hold on here. There's one at the bottom of this, number 5. All right, here we have function of x is 2 to the x power. All right, this right here, this is an exponential function. It's called exponential because, see, the x right here is in the exponent. All right, so we want to find f of 5. All right, so f of 5, remember now, this is my x value, f of this x. So I'm going to put 5 in for x right here. So I'm going to put 5 in for x, which means I'll have 2 to the 5 power. So f of 5 equals 2 to the 5 power. So we're just going to punch this in the calculator. All right. Now, when you punch this in, 2 to the 5 power, so 2. This button right here is my exponent button, this little triangle with no bottom, you know. So I hit 2 to the, and then see how it moves me up in there in the exponent? So I'm just going to put a 5 there, and there it is, 32. So my answer is 32. You see that right there, 32. Okay. Now, some calculators don't put it up in the exponent like this one does. Some calculators will just say 2, and you hit that button, so that button will be on there. And you'll just hit 5 like that. Okay? So your calculator may be like that. All right, number 6. All right, so we have another one. F of x is 5 to the x, find f of negative 2. So I'm going to put negative 2 in for x, which means I'm going to have 5 to the negative 2 power. All right, so when I do this, I'm going to have 5. I hit my exponent button. I'll just hit negative 2, and there you go. It's 0.4. Now, I think it wants a fraction, so I'm going to change it to a fraction, which is 1 over 25. And there's my answer right there. Now, again, some of your calculators, when you hit this 5 and the exponent key, you'll just hit negative 2, and you'll need to put that in parentheses more than likely, because if you don't, it could come out wrong. So you practice this and make sure you know how to punch these in. Now, number 7 and 8, we have some application problems with these exponents. And we have, like here, an amount of 235 milligrams of an isotope is given by this right here, where T is the time in years since the initial amount of 235 milligrams was present. Find the amount to the nearest milligram left after 59 years. Now, this is how we do carbon dating and stuff. We date things based on how much residual amount is left after, you know, so many years. We can calculate how old something is. But anyway, on this right here, all we're doing is we want to find out how much is left after 59 years. Now, T right here is the time in years since this isotope was given. So all I'm going to do is I'm going to put 59 in for T. All right, so let me show you how to do this. It's real easy. This is an E right here, which I don't really have a whole lot of time to explain that to you. But E is the natural base that we use for exponential equations. And it really is remarkable how this E number works out. And there's a whole lot of things you could look up on the internet, things about E, but it's really fascinating, that number E. E is like pi. You know pi is 3.14, and it goes on forever. All right, E is 2.71, and it goes on forever too, sort of like pi does. But E is a very fascinating number, but that's about all I could tell you about it right today. But when you punch this in, I'm going to hit 235, and the E button is usually on the LN button. All right, if you notice right here, here's my LN button, and you see the E is right there in blue. We'll get it a little closer there. There's the LN button, and see E is right there. So what I do is I hit Shift, the second button, to access that. So here's my 235. I'm going to hit Shift and then hit the LN button, and there's my E. And then it's in the exponent, so all I do is I do this negative 0.03, and then T is my years in 59, so I'm going to times by 59. And then there you go, 40.028. So the answer is C, 40. Okay. Now, again, some of your calculators, when you hit this 235 and you do E, then it puts a parenthesis or something on there. And so you'll have to put this in parentheses. So we're going to do negative 0.03 times my 59, and then you'll close it up like that. Okay? And that's how you would type it in. Now, if you have problems typing it in, you can't figure out how to type it in, contact me and I'll try to help you further, on how to type it in. Here's another question, similar. The number of reports of a certain virus. Right here in this pandemic, we're having a virus, anyway, this is how they figure out how this virus is going to spread. And so they tell us all the time that, hey, we're going to have this many deaths in this much time and all this. Well, they do it by these exponential equations is what they do. Anyway, this is the number of reports of a certain virus has increased exponentially since 1960. The number of cases can be approximated using this function. So here's the function right here. And that's since 1960, where T is the number of years since 1960. Estimate the number of cases in the year 2000. All right, well, how many years is 2000 since 1960? Well, that's 40 years. So I'm going to put 40 in for T of this. All right, so all I'm going to do is I'm going to type this in, and I'm going to put 40 where T is. So when I type this in, all right, it's going to be 354, and then I'm going to do my E, so it's going to be E, and then in my exponent, I'm going to have 0.005 times 40. And there you go, 432.37. So it looks like B here, 432. Okay, so that's not very complicated. You're just punching this in. And again, if your calculator does not put it in the exponent, see, mine puts it in the exponent here. Okay, if yours does not do that, you'll have 354. You'll hit your E button, and then it usually will put a parenthesis or something like this. So then you'll do your 0.005 times 40 in the parentheses. Okay? So that's exponential functions. Now, we're going to graph those. So if you look down here, these are graphs of exponential functions. Okay? Now, an exponential function does this. If you have like f of x equals 2 to the x, all right, it does this right here. You have this little tail that hugs the axis, and all of a sudden it hits right there on the axis, and this point right here is 0, 1, and then it just starts shooting up like this. Now, I wish I had more time to explain this further to you about how it does, but because there's some interesting things about this that we just can't really talk much about because of time constraints. But this point right here, every exponential function, no matter what your base is, hits this point right here. Because 2 to the 0 power is 1. 5 to the 0 power is 1. 68 to the 0 power is 1. So no matter what your base is, if it's to the 0 power, it'd be 1. So this point is on every graph. All right, so this is what the graph looks like. And then here's, if I go over 1, 2 to the 1 power would be 2. Okay, we're on these right here. 5 to the 1 would be 5. 68 to the 1 would be 68. And so this next point here would go up more depending on what the base number is. Okay, so this point is important on graphing it because that tells you about transformations, because that's what we're going to look at on this is transformations. So if I look at this one here, graph this exponential function. Well, look here, it's got transformations. See right here, this -1, that's going to move it horizontal, just like we've done before. See, because it's up here in parentheses with the x, basically. And then I got this -4, which is going to move it down 4. So this -1, remember, does the opposite. That's going to move it to the right 1. All right, so what we're looking at is, now, it's not going to be these two right here because they're going down and there's no negative. See, if it had a negative out front, that would make it go down. So that's not. So it's one of these two here. Okay. Now what you have to do is you have to look at your this line right here, this asymptote that it comes and approaches to. So both of these look like, is that 3, 6, 9, 12. These are 3s, so it's like right above that. So both of them look like they go down 4. Okay, because my little asymptote that I draw through here is just above that 6. See, this is 3 and 6, so it's just above that some. So it's B or C as far as that is concerned. Now, again, you can blow these up, but the thing you're looking for is this point right here. See, when this thing goes up 1 from the asymptote, when it goes up 1, that's what value you're looking for as far as how it goes left and right. So on this one here, this is kind of hard to tell. I think this one is right here. It's gone to the left. I think this one has. This one here looks like when it goes up 1, it's gone to the right. So I think C is my answer, which it is my answer. Now that's kind of hard to tell. Maybe I should do some of these on the screen so we can blow them up and look at them a little better. So that's what we'll do here. There's a couple of these. So let's do that. Let's look at this on the screen. Okay. So I can blow it up and you can see what I'm talking about a little better. All right, so here's one here. Okay, which one of these is the correct graph of this function right here? All right, so these two are out because they're going down. See, there's no negative in front of my 4 here. If I had a negative in front of the 4, then I'd be looking at these two. All right, so now this -1, all right, that's going to do the opposite, which is going to make it go to the right 1. Okay, this one looks like it's more to the right than that one. So I'm figuring this is my answer right here. But let's blow it up, make it big so we can see it better. Okay, so here it is, okay? I can move it around if I need to. All right, so you see it goes down to, now look here, this is 3, 6, 9, 12. These are 3s, and so you can see here I'm down 2. This is about down 2 right here. That's where this this has shifted down 2. Okay, so usually it's on the axis here, but you see it's down 2. All right, and then this moves it to the right 1. And so, all right, so since this is down 2 right here, okay, then down 1 would be about right here. Okay, so you could see that's shifted over to the right. So I'm saying down 1 would be right here, which would be up 1 from where the asymptote is. See, the asymptote is what this line, this tail is hugging. See, this tail hugs the asymptote, which is down 2. Okay, so you have an asymptote that this tail hugs. All right, so it's down 2, which means if I go up 1 from that, which is what we normally have on this function, that's shifted to the right. So that's my answer right there, A. A is my answer. I don't know if I explained that good enough for you or not. We'll look at 10. Okay. All right, so here's 10. All right, so on 10, we have 4, and look, there's no negative in front. So these that go down, like A and C, those are out. So we know it's either B or D. It's either B or D. All right, now look here. See this -2? That tells me the function's going to go down. So both B and D, you can tell they both go down too. Okay? And then what you're looking at is this +2. See this x +2 right here? Okay, that's going to make it go to the left. All right, it does the opposite here. All right, well, if you look at these two, this one looks like it's more to the left, doesn't it? This is going to the right. So the answer is going to be B here. Okay, the answer is going to be B. Now here, you could do this to make it bigger so you can kind of see. And what I'm talking about on this, see this asymptote right here? See, this is down 2. This is down 2. And so if I am down 2, okay, right here, well, if I go up 1, which would maybe put me here, that would be, up 1 would be down 1 now. And see where it's crossing right there, which is coming back this way too, it looks like. So yeah, that's the right answer right there, B. All right, so if you have questions about those, please, send me some questions and I'll try to help you all I can. If you go back to this paper here, we're just got a few more problems. This is number 11. Now here's a graph. Which one of these equations is the graph? All right, well, here's what you're going to be looking for. See my asymptote? Now they got the asymptote drawn here on this one, which is helpful. So what I'm doing is I'm looking for where this graph crosses 1 up from the asymptote, which looks like right here. See there, that's 1 up from the asymptote. That's that main point I was telling you about just a few minutes ago, and I don't know what I did with that paper. Here it is. See, this point right here is the same on every one of these exponentials. It's 0, 1. The asymptote is normally on the axis. Normally. So I look for that point right there. So see, you can see my asymptote is not on the axis here, which is gone down too. So you see, this is not right. This is not right because it's not going down there. These two right here go down too. See, -2, -2. But now this point right here, okay, it's going, I'm sorry, it's going back to the left 2, okay, and my asymptote has gone down 2, which means it's these two. So this has gone to the left 2, which means I should have the opposite of that. I should have x +2. I should have like my base x +2, which looks like C right here. C is my answer. So the asymptote being down 2 tells me it's one of these two. And then this one point that's up 1 from the asymptote, that's what I'm focusing on. And you can see it's shifted back to the left 2. So C would be my answer there. Okay, there's 2 more of these and we're done. On 12 here. All right, look at my asymptote. See my asymptote's up 1? So it's one of these two right here. These are out because those are, say, -1. So you look for that asymptote. That tells you it's one of these two. It's up 1. Now, look for that point that is up 1 from the asymptote. Well, if you look right here, right there it is. See it? It's up 1 from the asymptote. That's my main point that I'm focusing on. This point right here, it's up 1 from the asymptote. Okay? Usually it's on the axis here. Where's it located? Well, it's gone over 2 to the left, which means I'm going to have x +2 in my exponent. So that's A. Okay? And then 13. Look at 13, and then this is the last one. All right. Now, notice on this one, see my asymptote here and see how the tail is, and now it's going down. That means we got a reflection, so we got a negative out front. Every one of these has a negative out front. Okay, so every one of these, I can't rule out any because of it going down. But look at my asymptote. My asymptote's up here at 4 this time, which means I'm going to have +4. So it could be this one, it could be this one. This is out, this is out. All right, so you look at your asymptote, that tells you the plus 4. All right, now, since this thing's going down now, I've got to look for the point that's down 1 from the asymptote. So if I look at my asymptote here, see here's my asymptote, it's down 1, looks like it's right there. See, that's down 1 from the asymptote. Okay, usually that point is on the axis, but this time it's to the left 1, which means I'm going to have x plus 1 in my exponent, which looks like c. Okay. All right, so that's it for this inverses and exponential functions. If you have any questions, please contact me, and I'll help you all I can. So have a great rest of the day.